We've seen the laws of thermodynamics before. Let's have a quick revisit of the first law. In the simplest sense, the first law of thermodynamics states that energy cannot be created nor can it be destroyed. It can, however, be transferred from one form to another. Somewhere along the way, we learned about Born-Haber cycles, and we kind of restated the first law in the sense of, in a cyclic system, the total energy is conserved. So you go all the way around the loop, the energy involved in that transition is zero. But our text uses a specific terminology to determine what the first law is, and it says that the internal energy in an isolated system is constant. Okay, so systems can fall into three categories. They're isolated, closed, or open. And they're categorized by how they exchange matter and how they exchange energy. In an isolated system, it is closed to energy transfer, and it is closed to energy transfer. No energy gets in or out, no matter gets in or out. In a closed system, no matter gets in or out, but energy is allowed to be lost to the system or gained from the surroundings. And in an open system, matter can flow in and out of the system, as can energy. So let's have a think about what internal energy is. Internal energy is the total energy of the system. It's the kinetic energy component and the potential energy component of everything inside the system. It's also a state function, which means its value depends only on its form. It doesn't matter how you got to that position, it only matters on where that position is. And here's a restatement of the first law of thermodynamics, that the change in internal energy is equal to heat plus work. Q is heat, we saw this from general chemistry, and work. Work is when you move any object with mass across any distance. Energy is the ability to perform work. Just as heat is a transfer of energy, work is also a transfer of energy. It's the energy that is transferred when a force moves a mass, an object, across a distance. We're going to see this in terms of what's called pressure volume work or expansion work. I'm going to look at a couple of different types of expansion, but in general, the work that is performed by an expansion is the opposite of the external pressure multiplied by the change in volume. Here are some scenarios about pressure volume work. The first is what's called a free expansion. If your gas was allowed to expand into a vacuum, there would be absolutely no resistance to it doing work. So there's no external pressure that it has to overcome. Therefore, its work is equal to zero. In an adiabatic expansion, now adiabatic expansions involve no transfer of heat. So Q equals zero. And because delta U equals Q plus W, we find that the work is just the opposite of what the internal energy is. Now, there is a convention that work as expansion should be a positive value. It seems that our text allows negative values for this. I think we'll nail this down as we go through. Reversible expansions is just the form that we're familiar with, that the work is the opposite of the external pressure multiplied by the change in volume. And then the most complicated ones, isothermal expansions. So in an isothermal expansion, this is different than an adiabatic. These two are easy to confuse. In an adiabatic expansion, heat does not get exchanged. Okay, So heat's not allowed to come in or go out. So the temperature is allowed to go up or down, if you follow. In an isothermal expansion, what happens is the change in internal energy is zero. There is no change in internal energy. And so the temperature stays the same because we're allowed to have the heat flow in and out. So W here is equal to negative nRT, the natural log of the final volume divided by the initial volume. And we'll do some examples. Let's think back to general chemistry and calorimetry. We discovered that heat is equal to mass times the heat capacity times the change in temperature when we performed calorimetry inside a bomb calorimeter or an insulated cup as we did in lab. Well, this part right here, C, that represents heat capacity. Now, heat capacity has a very simple definition. It is the amount of heat energy required to change 1 gram of material by 1 degree Kelvin or 1 degree Celsius. Okay. Now, heat capacity itself changes as the curve right here. It reveals itself as the curve in the plot of internal energy versus temperature. Internal energy is not constant with temperature, and it's not linear. It has a curve because at higher temperatures you have more internal energy. That curve, the slope of that curve is the heat capacity. Now we have two heat capacities that we're going to see. One is Cp, that's the constant pressure heat capacity, and then this one, Cv, the constant volume heat capacity. I think we see this more than the constant pressure one. And Cv is just the change in internal energy divided by the change in temperature. Okay, now having said that, and making it sound quite simplistic, there's a little bit of a problem. And the problem is that heat capacity is used as a general term by many people, and it's not particularly well defined. So our constant volume heat capacity, Cv, is this thing right here. It's the amount of heat energy it takes to change 1 gram of sample by 1 degree Celsius. The molar heat capacity is the heat capacity per mole, and it's used in our book as just Cv and then a comma with an M. This little notation here tells you that it's now a molar quantity. Well, this is an extensive property and this is an intensive property. So that's a complicating factor. You have to get that right, because this one depends on amount, but this one doesn't because it's divided by moles. And then there is another term, specific heat. This one's quite useful. In introductory books, it's usually given its own letter, S, to mark it being separate from C. Our book has CVS, and the specific heat capacity is the heat capacity per gram. And because heat capacity itself is defined in terms of the heat energy required to change the temperature of 1 gram by a degree Celsius, this one comes in kind of useful also. Now there is some good news here. We don't have to find the values of heat capacity experimentally because we've seen enough that we can estimate them. Using the equipartition theorem, the energy of a system is shared equally amongst all degrees of freedom, specifically if you're a gas. And that there are going to be R over 2 for each degree of freedom. Okay, so when we look at a monatomic gas and we think about translation and rotation, we'll forget vibration for right now. That only becomes important at much higher temperatures. A monatomic gas is just a point, and it can go side to side and forwards and backwards and up and down. It has only translational degrees of freedom, and there are three of them, X, Y, and Z. So for a monatomic gas, CV is 3/2R. For diatomic gases, which are linear, you still have the three translational motions, but now you have rotation, an additional two of those. So CV is 5/2. For polyatomic gases, there is typically an additional rotational degree of freedom that gives us CVs of about 6/2. These numbers drift a little bit, and all the numbers are sensitive to temperature. If you go into significantly higher temperatures, then you will see these numbers no longer hold true. But it's a very nice simplification for room temperature. Let's look specifically at adiabatic expansions, just a little bit closer. In an adiabatic expansion, the gas expands, work is done, but no heat is allowed to enter or leave the system. And that means that the internal energy must decrease. And that means that the temperature has to fall. This is a key that expanding gases bring with them a reduction in temperature. This is how refrigerators work. So the adiabatic work, W, specifically for the adiabatic system, is equal to the constant volume heat capacity multiplied by the change in temperature. And then we've got a couple of relationships that we can use to our advantage. V1T1 raised to this power, which is the constant volume heat capacity, the molar version of the constant volume heat capacity divided by R. So V1T1 raised to that power is equal to V2T2, also raised to the power of the molar constant volume heat capacity divided by R. This rearranges so that you can find what the temperature, the final temperature is. So T2 equals T1 divided by, this is 1/2, V1 over V2. All raised to the power of 1 over this term, so R over CVM. This one kind of flips because it's actually 1 over CVM over R. Okay, this time right here. And then this guy, P1V1 raised to this power gamma is equal to P2V2, also raised to the power of gamma. And gamma is the ratio of the constant pressure, the molar constant pressure heat capacity divided by the molar constant volume heat capacity. And we'll do some examples of this. We'll work some examples.